can you run a fully autonomous AI agent locally on just a CPU? I want you to really think about that for a second. We're talking about a completely private, zero-cost AI agent executing complex tasks right there on your own machine. No expensive cloud APIs, no sending your personal data off to some external server. It really is kind of the holy grail of open source AI. And figuring out how this actually works under the hood is just absolutely fascinating. Welcome to this explainer. Today, we are unpacking a massive, real game changer in local artificial intelligence. We're going to explore the architecture and the practical implementation of bridging the gap between isolated local AI models and the outside world. By combining Ollama, which, lets you run models locally, with the new Model Context Protocol, or MCP, we're literally moving from basic chatbots to highly capable agentic systems. Here's our quick roadmap for the explainer today. 1. The local AI bottleneck. 2. MCP, USB-C for AI. 3. Bridging the transport gap. 4. The context window math. 5. Benchmarking small local models. And 6. Building your agentic system. Let's dive in. Section 1. The local AI bottleneck. To really grasp why we need a whole new protocol, we first have to look at the baseline problem. Out of the box, running a local model in a tool like Ollama is basically like having an incredibly smart AI in a box. It can generate text all day, but it has zero external reach. It can't read your local files, it can't search the web, it can't query a database. To break out of that box and actually do useful work for you, it absolutely needs tool calling. This is what elevates a basic text generator into a capable agent. And it's actually a complex multi-step process. The AI has to recognize a gap in its own knowledge, correctly choose the right external tool, format the exact parameters that tool needs, and then seamlessly interpret the results that come back. Moving on to Section 2, MCP, USB-C for AI. Historically, giving an AI tools meant you had to write custom, fragmented integration code for every single database or API you wanted to use. It was a nightmare, but that has completely changed with the Model Context Protocol, or MCP. It's an open JSON RPC-based standard. Think of it exactly like USB-C, but for AI. Instead of writing custom adapters for every single tool, developers can just write an MCP server once and boom. Any MCP-compatible AI client can immediately connect to it and know exactly how to use it. It's a universal language for tool integration. And in practice, this ecosystem is already exploding. By plugging these available MCP servers into your local model, your AI can suddenly read and write local files right there on your hard drive, using the file system server. It can execute complex database queries with SQLite, browse the live web with Brave Search, or even manage your org's repositories via GitHub. And the best part? Because you're running the LLM locally, your private data and file paths are staying right where they belong, on your machine, not beamed up to some cloud provider. All right, Section 3, Bridging the Transport Gap. Now, you might be thinking, awesome, let's just plug these MCP servers directly into Ollama and get to work. Well, if you try that, it breaks. And it breaks because of a massive architectural conflict. See, MCP servers, by default, communicate over standard input and output, or STADIO. That requires a persistent, stateful, bidirectional pipeline. They act as persistent local subprocesses. Ollama, on the other hand, operates as a stateless HTTP server. It just handles one-off web requests. A stateless HTTP endpoint cannot natively maintain that persistent connection required by an MCP server. They are just fundamentally incompatible at the transport layer. So how do we fix this transport gap? The secret sauce is specialized middleware that sits right in the middle and translates between the two. We've got 3 powerful options paving the way right now. First up is ollmcp, which is a Python-based terminal interface. It dynamically connects Ollama to MCP servers and offers amazing safety features like human in the loop. Then you have Kit. This is a Go-based tool that uses an embedded interpreter to run extensions directly in process. That's huge because it completely avoids the overhead of constantly spawning new operating system subprocesses. Finally, there's msipo, which acts as an HTTP open API proxy, converting those local tools into secure REST endpoints. Honestly, these middleware clients are the hidden heroes making local agents possible. Which brings us to Section 4, the context window math. Okay, so we've solved the network connection, great, but now we hit a severe cognitive limit. Take a look at this formula, SP equals CB plus sigma TI. This explains exactly why feeding tools to lightweight edge models is computationally dangerous. SP is your total system prompt size. It equals your base prompt plus the sum of the token sizes for every single active tool schema you've enabled. Think about that. Every time you submit a prompt, the entire JSON schema for every available tool must be injected directly into the model's context. If you load up, say, 20 tools, this rapid linear scale of token consumption will completely crush the context window of a sub 4 billion parameter model. It literally leaves almost zero room for your actual conversation. It's total cognitive overload.
Section 5. Benchmarking small local models.
So if we're running on a CPU with a limited RAM, we absolutely have to use small models. But who actually survives that context math we just talked about? Well, the true test of a small model isn't just knowing how to use a tool, it's knowing when not to use it. We call this tool restraint. Check this out. Notice how Llama 3.23b really struggles here. It has very low restraint. It's basically a hammer that sees every prompt as a nail, trying to call tools even for basic, everyday conversational questions. Qwen 2.53b performs much better, high restraint. But the unexpected winner? BitNet 2b4t. It's an instruction-tuned, ultra-lightweight model that shows near-perfect restraint, outputting precise JSON tool calls in just over 2 seconds on a standard CPU. Incredible. If we take a little deeper into the architectural quirks behind those results, we see that small models are highly sensitive. Google's default Gemma 2b, for instance, it often requires heavy chat template modifications just to force its tokenizer to spit out properly formatted JSON. Otherwise, it just starts hallucinating tools. Qwen 2.57b, however, natively understands schema parsing right out of the gate, making it a top recommendation for local use. And Llama 3.23b, while it's fantastic for terminal loops, is really prone to routing errors if two tools have similar descriptions. The takeaway here? You've got to know these quirks when you're picking the brain for your agent.
Finally, Section 6. Building your agentic system. Let's bring all this theoretical architecture and model data together into one final execution loop. It's actually a beautiful self-contained cycle. Step 1, you ask a question. Step 2, the middleware client sends your question along with those heavily optimized tool schemas over to Ollama. Step 3, the model calculates if a tool is even needed. Step 4, if yes, the client intercepts the model's decision and securely executes the local MCP tool. Step 5, the client takes the raw results, maybe it's a folder directory list, and feeds that right back to the model. And step 6, the model reads that results and generates a final natural language answer for you. But hey, before you go spinning this up on your machine, you need a defensive engineering checklist. Because small models can and will get confused and enter infinite loops. And you definitely, for sure, do not want an autonomous agent infinitely deleting your file system. First, strictly limit your active tools to preserve that precious context window. Second, use tools that enforce strict line-based file reading. Don't let it dump an entire megabyte text file into the prompt. Third, seek out community-optimized models specifically tuned for tool calling, like customized GGUF adapters. And most importantly, use middleware that supports human-in-the-loop, or HIL. This pauses the AI right before it executes a command, so you can approve or deny the action. Safety first, always. Well, there you have it. We've covered the bottleneck, the MCP standard, the transport layers, and the models that make it all happen. You now have the exact blueprint to run a completely private, zero-cost, autonomous AI agent right on your own CPU. The technology is here, it's open source, and it's incredibly powerful. So the only question left to ask yourself is, what are you going to build now? Thanks so much for joining me on this explainer, and happy building.